Have you ever really stopped to wonder what's actually going on inside your phone or your laptop? I mean, we're surrounded by this amazing technology 24/7, but the process of creating its brain, the microchip, is seriously one of the most complex things humanity has ever done. Okay, let's dive in.
So let's just take your smartphone. Inside it, you've got something like 62 different microchips. And on those chips, get this, there are about 90 billion transistors. No, that's not a typo. 90 billion. These are the tiny little on-off switches that power our entire digital world, and they're all crammed into a device that you can just slide into your pocket.
And that really brings us to the big question, right? How on earth is it even possible to build billions of components that are so small they are literally invisible, and then assemble them all into this perfectly working three-dimensional maze?
To figure that out, we're going to go on a little journey. First, we'll peek inside the digital universe of a single chip. Then we'll explore the nanoscopic labyrinth of how it's built. We'll unpack the wild 3-month recipe it takes to make one, meet the giant machines that do all the heavy lifting, and finally see how a simple silicon wafer becomes the finished chip you can buy in a store.
All right, let's start that journey. Imagine we are zooming way in, past the keyboard, past the computer case, and right onto the heart of the machine, its central processing unit, the CPU.
And here's what's so wild. A modern CPU isn't just one thing. It's more like a whole system on a chip. You've got multiple processing cores, you've got a graphics processor built right in, memory controllers, dozens of specialized parts all working together in perfect harmony.
But let's go deeper. If we zoom into just one of those cores, we find this incredible 3D structure. It's not flat at all. Down at the very bottom, that's your foundation, billions and billions of transistors. And then, built on top of that, is what looks like a 17-story skyscraper made of tiny copper wires, all shuttling data back and forth. It's like a tiny city.
Okay, so just how small are we talking here? Well, a single transistor is about 50 nanometers wide. To put that into perspective, because the numbers are kind of mind-bending, that's 10 times smaller than a single mitochondrion inside one of your own cells. And it's about 1,500 times smaller than the width of a single human hair. We are truly operating on a scale that's hard to even imagine.
So, how in the world do you build something so small and so ridiculously complex? Honestly, the best way to get your head around it is with an analogy. I want you to think of it like baking the most complicated cake in the history of the world.
This is the real challenge. Each microchip is like an 80-layer tall cake, and every single layer has its own unique, impossibly intricate pattern. The recipe has almost 1,000 steps, and it takes 3 full months to finish. But here's the craziest part. There's absolutely zero room for error. If you mess up just one measurement by more than 1%, the entire cake is ruined. You have to throw the whole thing out.
So to build up all those layers, they basically run the same 6-step process over and over and over again. First, you lay down an insulating material. Then, you coat it with this light-sensitive chemical called a photoresist. You shine ultraviolet light through a stencil to burn a pattern into it, and then you etch away the parts you exposed. After that, you fill in all the little trenches with copper, and finally, and this is critical, you polish the whole surface until it's perfectly flat, just so you can start all over again for the next layer.
So, we've seen the tiny microscopic recipe. Now let's zoom back out and take a look at the kitchen where this incredible cake gets baked. It's called a semiconductor fabrication plant, or just a fab for short.
And the scale here is just, well, it's nuts. We are talking about a clean room the size of 8 football fields. Inside, wafers of silicon spend 3 months moving between 435 different massive machines, completing almost 1,000 distinct steps. A single factory like this can churn out about 50,000 of these finished wafers every month.
So what are all these hundreds of machines even doing? Well, you can pretty much group them into 6 main jobs. Some are just for making the stencils or masks. A whole bunch are for either adding material to the wafer or removing it. Others actually modify the silicon itself. And, critically, a ton of them are just for cleaning and inspecting the wafer at every single stage.
But out of all of them, there is one process that is the absolute king. It's called photolithography. This is how the chip's design actually gets printed onto the silicon. You can think of it like the world's most advanced and precise projector, using extreme ultraviolet light and a stencil to beam down a pattern. And they have to do this over and over, up to 80 separate times for a single CPU, once for each layer. So after all that incredible technology and all those steps, what do you get? Let's talk about the transformation of how you turn a simple piece of silicon into something, well, something priceless.
Okay, so this is where it all starts. A 300mm wide disk of perfectly pure single crystal silicon. I mean, this thing is already a marvel of material science, but at this stage, it's worth about $100.
Now, fast forward 3 months, after that grueling journey through the fab, that same $100 wafer is now worth around $100,000. That transformation makes the finished wafer, by weight, about 10 times more valuable than solid gold. It's just insane.
But here's the catch. Manufacturing at this scale is so unbelievably difficult that not every single chip on the wafer comes out perfect. Tiny defects can knock out a core here or another section there. So what do? They test every single chip and then sort them into different piles based on how well they perform. This whole process is called binning.
And this binning process is exactly how companies create an entire product line, like the Core i9, i7, and i5, from a single wafer design. The chips that come out absolutely flawless, all cores firing at top speed, they become the top-of-the-line Core i9s. The ones with a few disabled cores, they might get sold as an i7 or an i5. So the next time you see different tiers of processors, remember, they were often literally born on the exact same piece of silicon.
All right, we are on the home stretch. We've built all the circuits on the wafer. Now for the final stage, turning those tiny little squares of silicon into a product you can actually buy and put in your computer.
This all happens at a totally separate factory. First, a laser slices and dices the wafer to cut out each individual chip. Then, that chip gets packaged. It's put on a little substrate so it can talk to a motherboard. They stick a metal hat on top called a heat spreader for protection and to keep it cool. The whole thing gets tested one final time, and then into the box it goes.
And that's it. The journey is complete. You go from a $100 wafer of silicon to this incredibly complex device that's ready to be the brain of a computer. And it's this mind-boggling process that enables the massive computational power we need for everything from sending an email to running the advanced AI that is fundamentally reshaping our world.
You know, when you really think about it, we are using machines the size of city buses to build structures thousands of times smaller than a human hair. We are pushing the absolute limits of physics. And that leaves us with one last big question to chew on. If this is the monumental effort it takes to build the technology of today, what in the world will it take to build the technology of tomorrow?